nanohub.org.
Online simulation and more for nanotechnology.
All right. So today it would be the last class for this 5-week module, 1-credit module, and I would continue this discussion on machine learning. Machine learning, as you remember, that this is a way of actually describing data where you know input and output, and you want to describe the data based on some statistical principles. Within these 5 weeks, we have actually gone through the development of this field for last 100 years, starting from Fisher's time and onward. So in many ways, what you learned in this course is modern understanding about how to handle data, be it large or small. So today's discussion would be something that is in some way at the cutting edge of this topic. You know, this word machine learning is very popular. The new word is physics-based, and this is something I feel that without this initial piece, machine learning is sometimes not only counterproductive or not very useful, but it can be outright dangerous. If we use machine learning to do engineering design without appreciating the physics associated with it, it can be a very dangerous application, and we should be careful. So we will start with the general understanding that why I said so. What's special about physics-based machine learning? And then I'm going to explain to you 2 examples. One example is dropping a ball, like just an apple or something, in the real world. The keyword is real. And then the second one is also another very interesting example that is still not published in that general sense, but it is in the archives, this lake temperature distribution. And again, I want to explain what it means and how people are working on it. Now, another approach other than machine learning, people didn't used to call it machine learning, it's called structural equation modeling. That would be the second physics-based approach, and I want to explain that. That is actually predates machine learning, but actually people have not paid that much attention in the machine learning context, but they are coming back now. Many people are coming back, and I will explain why, and then I will conclude. You know, I started this course with some pictures and with some calculations from Galileo's notebook. And in the Galileo's time, in some way, as you know, that this is sort of predates Newton. So there was no notion of gravity, no notion of all those sophisticated understanding about how 2 bodies attract each other, and long before general theory of relativity. So what he was doing, and he was a very remarkable experimentalist, and what he did was this is a plane from which things are being thrown. It's like a projectile, and it's a little inked ball or marble of some sort, and you are giving it a different initial velocity, and of course you cannot see it. In those days there was no flash photography, so these pictures are not really therefore were drawn, but the place where it landed on the sand, those had black color in it, because it was covered with a black paint. And from that, he could, for example, think about the trajectory, because the different amount of initial velocity would give him the different distances. And you can see that therefore he was taking an empirical approach. He did not know why things are parabolic, but simply by taking the endpoints and fitting it with a parabolic relationship, he could begin to make predictions. So machine learning is in many ways very similar. The input here for this problem are of course gravitational constant, which he did not know. Of course the height Yes, he knew that. The radius of the ball, yes, he knew that, but how it affects things, he did not know. The friction, the drag coefficient, and the density of air, these things are, of course, all controlling the placement. And what he was trying to do was to sort of look at the time or the distance it took to fall here. So this is in some way you can say that this is classical machine learning. Ptolemy's model of how the planets go around, that's exactly, it's so accurate that it's just all observation, so accurate that modern planetariums all use the same Ptolemy principle to actually project the night sky. So in any way, the bottom line is that this is a purely empirical approach. Now, if Newton was at that time, available at that time, or if he were born a few hundred years ago, then of course he would have said to Galileo, you can imagine the conversation, that no, the reason this is having this projectiles is because there is something called a gravitation. This is an acceleration, mass times the acceleration is related to the force, and so therefore you can calculate the time needed in order to, if h is this thing, then g is the gravitational constant, then you can essentially calculate how long it's going to take and how far it's going to travel, and so on and so forth. That's something you learn in high school. Now, in some way, this is much more predictive, because after you know this rule, you can do something much more impressive, like how they explain how long does it take for the planets to go around the sun. You can calculate all those because that's a constant falling. The planets are constantly falling towards the sun, but it just is missing all the time. And you can do many more things because you now know the physics. But even when you thought that you got very sophisticated, Newton could not really account for, at least in his time, could not account for the radius. Yeah, sort of could. But the radius meaning that if you have a ball, the ball with point which is closer to the earth will have a little bit more gravitational pull compared to the point which is farther out. So therefore, everything he could do was point sources. Think about the planet as a point. Then he could calculate. Other calculations are much more difficult. If you have three bodies, two planets, one on top of each other, one being influenced by the other one, Newton would have a hard time to solve those problems, right? That's how Pluto? That's how the Pluto was discovered. But the bottom line is that even when you think that you know the physics, that you really don't know, you know an idealized version of the physics. You really don't know the real physics completely, because it's often difficult to account for the drag and then rotation of the earth, then this being a finite ball and all sorts of things. So therefore, we always idealize the world, and we have been very successful at that. But the question is that even in that, physics doesn't capture the full complexity of the real world. So what would be best is if we could have, for the real world, if we could have a combination of both worlds. For example, if you have only a few pieces of data, you don't have a lot of data, so you have a low usage of data, big data, higher and small data, then physics-based models are very good. And in the physics-based model, generally, you use the theory to a great advantage, right? You generally use it for great advantage. On the other hand, if you have a lot of data, but not that much understanding. For example, why people buy one phone when they already have another phone? There is no physics explanation for those things, but there is a lot of data. So you could predict that in the next cycle, how many phones will be bought, right? So therefore, that will be a black box neural net or black box machine learning, the one that I explained in the last two classes in terms of backpropagation, in terms of deep learning, quote unquote. You realize there's nothing deep about deep learning, right? So the base would be, if in some way we could combine the best of both worlds. So if we could do that, first of all, the network that needed, the neural network or artificial machine learning network that we needed would be considerably smaller. I'll explain that. And this we'll call physics-guided machine learning. And that would be much more powerful. This is an emerging topic. And but you get the idea that then generally that would be a good starting point. So what I'm trying to say is that there is a distinction between, in both cases, input and output, both cases. But here in one case, this is purely statistical. So what does BBNN stand for? I have to remember what this is. So BBNN, so it will be black box neural net. So that is purely, curve fitting. Glorified curve fitting, very useful. I'm not saying anything bad about curve fitting, but this is curve fitting nonetheless. But in the other approach, what you do is that given the input, you try to extract the physics, whatever is the physics problem, and then you also and then that output you send it in here. And this physics-based neural network, what it will do, it will get two input. One is this unvarnished input, and another input it will get is the sort of the output of the physics prediction. And it will just try to develop the neural net based on the difference. The difference we'll be focusing on. And so therefore, if we make a mistake in the difference, well, in that case, everything will not be wrong, because it is a smaller problem. The main part of the physics is still there. But if it begins to, this is also very interesting. For example, if you drop a ball in the air, then it is one thing. Then your results would be pretty good. This physics-based neural network would be pretty small, and that will be very good. But you see, this also has another advantage. Let's say you take a bunch of balls and drop it in water. In water, it will behave very differently, because it will immediately get to after a few seconds, it will get to the terminal velocity. And in that case, if you try to feed that data, because you don't know, you're assuming a physics of ball dropping in air, but actually this is a physics really involves ball dropping in the water. So in that case, what will happen, you will immediately see that your predictions are getting wrong, and this network is growing. And anytime that network begins to grow, you know that you need to relearn the physics, because you have used an incorrect physics. In the extreme case, if your physics is completely wrong, this will be thoroughly worthless, and this will become the same as the black box one. So this will give you an idea that when you are sort of getting out of the physics zone and really getting into curve fitting zone. So let me then give you some specific examples. For example, in this particular case, what I have here is I have a ball at a distance h from the earth, and I want to know how long does it take for this ball to drop. And you have seen it in high school that this is essentially derivative. This is the acceleration, and acceleration is equal to g, right? And minus g is because your g is sort of measured in this direction, and your acceleration is in this direction. And so therefore you can then calculate, and you want to know when z is equal to 0, because that's when it's a second order differential equation. So therefore this is the solution, and you want to know when z is equal to 0. When z is equal to 0, well, you set it equal to 0, and that gives you the time for the arrival, and you know that 2h over minus over z, that will give you the square root of that. That tells you how long it takes. Of course, this is already a significant improvement, because if you didn't know this, then if you are doing an experiment in the earth versus if you are doing an experiment in the moon, if you didn't have that, you have to relearn. You have to redo the machine learning. You have to retrain the network again. But if you know this, you know the physics, and so therefore there's nothing to be relearned. Once you know how to measure g, then you immediately know what the answer is. But as I said, that this is an idealized one. In real world, this will not happen because, of course, depending on this H, the density of air can vary. Like say you're jumping off, you're a very adventurous person, you're jumping off a plane because you have nothing better to do. And so therefore, you are, but of course the density of air could be changing, the temperature of the air could be changing, the humidity of the air could be changing. So all sorts of things that could be changing, and that is very difficult to include. You can do it numerically, but think about how many measurements you have to make. And that could change from time to time. So therefore, doing this, yes, it is possible in the real world, but may not always be very feasible and very useful. So in that case, you would like to probably just do the ideal part and fit the rest with machine learning. Now it turns out that actually people have a lot of time. At least in old days, they didn't have computers, so they actually could spend some time thinking about solving differential equation in their spare time. And one thing they could do that instead of assuming a point source, you could assume that it is a finite thing. And if you assume it's a finite thing, then of course you can have, and depending on the distance, the gravitational constant would change a little bit. The force will change a little bit, right? You know, m1, m2 divided by r square. So when the ball is getting closer and closer together, the forces are going to change a little bit. Generally, we ignore it because the radius of the earth is so much larger than the apple tree that you have. So that therefore, we generally don't account for it. But in principle, you could, if you drop it from a high distance, you can account for it. Unfortunately, in this particular case, it turns out that you have a numerical solution. And yeah, you can, or analytical solution. And if you like, you can expand it and then calculate the coefficients. But what I just want to tell you right now is that these are all nonlinear functions. These are nonlinear functions. So as you introduce more and more non-ideal effect, then your computational cost is going to go up very, very quickly. And so therefore, you have to be careful about how real do you want to make it real. So that's something. This is a very interesting paper, Dimensional Analysis, Falling Body, and the Fine Art of Not Solving Differential Equation, because this one tells you how to solve problems without solving them. Now, if you want to do air resistance, well, things are getting really interesting. You know, this is the same velocity. Velocity is the time derivative of acceleration. So dz dt would be the velocity, and I'm writing the same Newton's law. But this time, the reason I'm writing it in terms of velocity is because I want to include friction. And the friction is proportional, is a force. Friction is a force, so I cannot write acceleration directly. And the friction depends on how big the area, cross-sectional area is. That's why when you open up the parachute, then the velocity, falling velocity reduces, is because all of a sudden you had whatever, maybe 1 meter square, not 1 meter, 1 feet square or something of your size, and all of a sudden it appears that you have a giant size, right? That's how the thing works. And then what happens, the G doesn't matter. I mean, these two can essentially balance each other, and you don't have a high fall velocity. But anyway, yeah, you can, again, this equation is a nonlinear equation. Again, you can solve it. When you solve it, you can get an expression for velocity that has tan hyperbolic of different sorts, square root, and all sorts of things. So bottom line, complicated function. We can all do it, and especially we can do it if it's given in exam time. We can do it as homework. But the thing is that this is not really very useful, in the sense that very few people would actually do it on their own. So, and then if you wanted to include these two together, velocity, I mean, this is the friction, and this is the distance dependent force. Now you are saying this is probably not a solvable problem anymore. Now you have to bring in a computer and actually solve it. So the important point I want to make, that most thing is that here people would say, assume something, that the friction coefficients is actually independent of height, which you don't know because the temperature is changing, so you don't know. So you are making an assumption anyway. If you are making an assumption, then you cannot solve it by computers. You have to do finite difference and all sorts of things. Maybe it's better not to solve this problem this way. There is probably you can get equally good information by doing something slightly different. That is, do this physics problem as an idealized problem and say that everything else, this friction and other things, these are sort of the extra correction on top of that, and do a machine learning on that, and then add them up to see what your solution is. That way, your machine learning, you have taken out a big chunk from your idealized time, falling time, and then that will make your machine learning very, very fast. And in some cases, when I wrote a small code, I found that the time that you need to evaluate all this cosine hyperbolics and all, you could train a little machine learning few node problem faster than that. So therefore, there's nothing wrong in this approach, especially because you have a computer. So why not use it? So this is one. This is one thing, that this is how you think about, you use machine learning for this problem. The second one is a even more elaborate problem. And this is sort of, I found it very interesting. And I will tell you again in a nutshell, just to give you an idea about how to think about this problem in a new way. The problem involves predicting the temperature as a function of depth-dependent temperature of a lake. Now, why do you care about this depth-dependent temperature of a lake? Because it turns out the temperature of a lake is the master variable. That means that whether the algae and other things will thrive in the bottom, whether the fish will grow at a certain, fish population will grow at a certain rate. It's remarkable that how sensitive it is. So it's remarkable that every temperature zone essentially supports a function. And the whole thing is a network. It's an ecological network. And you need to know the temperature depth dependence temperature to know whether this is healthy or not. And at what point you have to sort of intervene. That's what the National Forest Service and other people do. They have a deep understanding about these things. They make measurements on the surface temperatures, and then they have model. What type of model? It is a little bit of empirical model, but like a Newton law model, meaning that what they do is that they have a body of water, they do an energy balance. So they will write a, let's say, a COMSOL or a finite element model of some sort, and capture that in analytical form. They will do flux balance about how much sunlight is coming in, and the infrared is getting absorbed, and then at what depth that does the light go through, and so on and so forth. So they will have a model of that. They will also have a model of flux balance, not only energy balance, but flux balance. So what does it mean? Flux balance means that how much water you already have, whether there is a rain or whether there is a evaporation going on. So that you remember, right, in California, the reservoir water a couple of years ago, they reduced to a dangerous low level. Now they have come back up. So all those things. So there you can write equations, and there are empirical equations. And people often would make, those people would make more than 10,000 measurements, but of course you cannot go everywhere. So what you do is you measure the surface temperature. And these are done over 20, 30, 40, 50 years period. And they have gigantic databases in which they keep this information. So it turns out that you can do a neural network based on this, but you can immediately see that you will get into real trouble. Think about how many variables, input variables, do you really have to account for. You have to account for the depth, first of all day, because it depends on the season, and the irradiance from the sun, and the depth, how deep are you, and what type of absorption is going on. what fraction of short wavelength, what fraction of long wavelength, relative humidity, how much rain, and so on and so forth. So there are a whole set of inputs will now feed your neural network in here. And then here you have only partial information. You have only surface temperature information. And then you try to develop this black box neural network model. But you can immediately see that there could be many combinations of this that can give you the right surface temperature, which could be completely wrong when you go down in water. Because not completely wrong, but there's no guarantee that those will be correct. And if those are not correct, the corrective things that those officials will take, like adding maybe more food for the fish or doing something about it, that would be completely wrong. So this is an engineering problem, and machine learning is not a good way to solve engineering problems. Yeah, advertisement, recommendation, those are also have engineering aspect to it, but in the algorithm side, not in the formulation side. So for example, you know that how physics then comes to rescue. For example, you know how the density of water changes as a function of temperature. We know that, right? Density of water, of course. What temperature is the density of water? The max. 4 degrees. 4 degrees. And that's very important, right? For some strange hydrogen bonding, this happens, right? 4 degrees. But 4 degrees is essential to sustain life. Because if it were not 4 degrees, then the ocean would freeze. And the ice would go all on the bottom and everything would die. And yet, everything survives because of this strange requirement that at 4 degrees or so, generally it has the lowest densities, the snow floats, right? So, but you have to be able to, whatever you do in here, whatever combination of parameter you know this is a fact. And so therefore, y is the temperature. So therefore, whatever you do, you have to be able to make sure that this relationship between density and the temperature is respected. It has to be respected. The second thing is, physics tells us that for normal water, as you go deeper and deeper, the normal water, the density increases. You cannot have a situation where the density is higher and then it goes down in the opposite direction. And yet, if you use a black box based machine learning, there is no requirement. Only thing it does to reduce the loss function, reduce the error. And so there is no requirement whatsoever that this profile is correct. So what do you do? What do you do in that case? So what it does is that, so therefore this is a failure where you have a loss function. By the way, let me just, loss function is what I already explained to you before. Remember the prediction and actual observation, square of that, right? But of course, do you remember this issue about AIC? AIC, what was AIC all about? AIC and BIC is that you have to, if you don't want to use too many parameters. AIC sort of encourages you to use fewer parameters. And so that is in here. And lambda is something that you know about. Anybody remembers that when you have an optimization problem, what is lambda? Lagrange multiplier, right? Anytime you want to do a constraint, do you remember that when you were doing Fermi distribution, then what was it? We wanted to make sure that energy is conserved and particle number is conserved, right? So therefore, we had that Lagrange. So you account for this AIC so that you don't start making bigger and bigger and bigger network, because bigger and bigger network will give you better fit on the surface temperature, but it will become less and less predictive. So therefore, you use some sort of AIC based approach to constrain the growth of the network. That's good. But what the physics says that in addition, you must respect the physics facts. That is, that every point which is higher must have lower density compared to every point which is lower. That's physics. And so therefore, if you don't account for that fact, so you see now you have introduced a second Lagrange variable, and that is called lambda physics. And this loss.phi, this is how you write it in Python, because, right, that's how you write Python variables. But the point in there is that you would say that the temperature, the density, I should have written rho. The density at this one, at every point, it must respect this relationship. Any prediction that does not respect this relationship will be thrown out. So therefore, when you sort of have this thing built into it, and then you build a machine learning model, this is have a much higher chance of being reasonable. And this is exactly what they found. So I'll walk you through these two examples just to, because this makes several important points. The people were sort of thinking about two lakes. These lakes where there were thousands of surface temperature measurements were available. And then there were also, also it's available in open database. And so therefore people try to make, see whether how good machine learning would work in this particular system. What you are seeing here on the y-axis is test. What is this? RMSE. So residual mean squared error. What is it? Root mean squared error, right? Square root of all the loss function that you have, whatever is the residual. So that's what you have. And by physical consistency, what it means, that whether it respects that curve, whether that higher density at a higher density at a lower depth versus the other way around. So how accurately, so 1 means physics is gone. There is no consistency whatsoever. 0 means at every point you ensured that it is consistent. You did not violate it. And this is the error. So there are 5 methods. By now, you know at least a few of them. First one is SVM. Does anybody remember, based on the discussion in the last class, what is SVM? Support vector machine. You see, you are already a machine scientist. So anyway, so support vector machine. And in the support vector machine, I said that that's very good for classification and learning. Look at that, where this is. This is in here. That means it does not do physics, does not respect physics very much. And nor does it have too low an error. Because you're just, maybe if you made the network even deeper, with 600 layers, maybe it would have done better, but this is where things are. Pure neural network, this is the green one. If you do pure neural network, then, because remember, what is neural network? In that case, it works with the label data. So if you do label data rather than just classification, then your error goes down, but again, you will violate the physics. And so therefore, your decisions made out of these data is likely to be incorrect. And it's not probably a good idea. So these 3 things, but if you try to do pure physics, just like Newton did, idealized point source, yes, then in that case, this physical consistency is guaranteed, but the error is not 0, because there are important variables that your pure idealized model did not capture, like the friction of air. If it didn't capture it, you cannot expect that the error will be very less. And by the time when you have everything together, this physics-inspired neural network, then you can see at least it is pretty good compared to other methods, right? Then this is in the lake 2. In the lake 2, correspondingly, you can see on the very left corner, very left is good, right? Good physics, low error. And so therefore, on the very left corner, you have these methods which sort of works out. Now, this says there is a distinction that it is physics guided, neural network versus 0 and physics guided neural network, what is the difference? The difference is, in one case you insert this, but you don't account for it in your loss function. That there's no penalty for being wrong in the physics side. So that is that 0. And if you insert a penalty, you're doing the network the physics way, but you are not inserting a penalty in the loss function. So there is two ways you can do it. One is with this model, but in one case you don't insist on it. If you don't insist on it, then you can see that you'll be physically wrong at some point because you didn't insist on it. And that's what these models. And you can see that it doesn't, if you don't have a cost function associated with it, then of course sometimes you will violate the physical consistency, right? Yes.
Is it like giving feedback from delta y to the physics?
Of course, of course. Every time, remember how the back propagation works, that every time it does not approach to minimize, then you have to adjust the coefficients until the error is minimized. And with that Lagrange for the physics thing, it will keep insisting that otherwise it will give you a big penalty. So that will keep insisting that you reduce that part before you do anything else. All right. So this is good, but at least in here, Newton is you have Newton, or you have other people who know the physics is helping you. But sometimes you don't have Newton, like it's not pure physics problem, but you sort of know the cause and effect in some way. The question is, can you do better than classical machine learning? So that's what I'm going to explain to you. When you when you go to an emergency room, which I hope you will not have to go with, they generally ask you to fill up a table or information that how are you feeling in between your pain between 1 and 9, how bad is your pain? Subjective information. So you generally fill up a survey. Now, when you are filling up this survey, what you have is a set of input, pain and this and that, and a set of output. Now, two people may not say that they have equal amount of pain. When I go to the doctor's office with a little bit of pain, I am sort of putting 9 over there. My wife goes at the same time, she puts a 3 over there. So it's all relative, right? So therefore, what is there is an input hidden variable. There are a set of hidden variables that makes this input-output different. And what the structural equation modeling does is try to figure out in a systematic way what these hidden variables are. For example, artificial neural network essentially is a one-directional thing. Yes, you have back propagation to fix this, but it generally goes from the input to the next hidden layer, then the next hidden layer until it goes to the output. That's how it sort of propagates in one direction. But you know that that's not always correct, because what you may have is that you may have a reaction that is forward and backward, right? Redox reactions. You have a reduction and you have oxidation. So therefore, anytime you want to represent a redox reaction this way, you are asking for trouble because you are throwing away a very important piece of information. So what you can do is essentially have far more connections, and also there is no relationship between nodes on a single layer, right? But yet you can have a system where they are dependent on the simple layer. If you don't account for it, then this machine learning thing will keep growing. And but because you are not doing the physics correct, of course it's going to grow. But if you account for this physics properly, then the hope is that the network could be significantly smaller. Moreover, we explained that all of them are straight lines, right? Do you remember? That machine learning means being able to draw straight lines. That's how I said it. But of course, if you have a e to the power ea over kt, no straight line will catch it. right? It's an exponential function. How can you just do? You'll need many straight lines in order to represent that one. So this relationship, as soon as if you always put it as a straight line, may not be the best description of the system. So therefore, the structural equation model, this structural SEM, is not the scanning electron microscopy, not that. This is structural equation modeling. And it turns out that there are many softwares for doing this, and this is how it works. I'm going to explain to you. So let's say there is a emergency room nurses, and often they are very stressed because they have to sort of go through, take care of so many people. And from time to time, they may fill up a form to think about how things are going, and that form may have information that how much bending work they are doing. So the nurse may fill out that he or she had to do a lot of them. So between 0 to 10, how much? The person may say 9 or things like that. And then, so on, how many hours does she have to work? She may give an estimate. Like if I give you an answer that how many hours do you do research, you would say 12 hours. But actually what happened is a different story. But you may have a perception that, and we all overestimate how much we work, right? Especially professors do. The way you do it, you define the individual constructs. This means you think about what could be the input and output. Then you develop a survey of some sort, and you design a study, and then you get the survey results. So what are the survey results? These are your survey results. These are your survey results. And what you're trying to get, because this survey results doesn't tell you how to improve things, anything at all. But the way it is going to improve is that there must be some hidden variable, meaning that some people may have a bad posture. That's leading to that person's back pain, for example. Or it can be that that person is always in the first person to come if somebody came with a heart attack or this and that. Somebody may be the second layer person. So the first layer as responders, they are always highly stressed. So their relationship. So what you would do, you would guess without all these errors. You have all this information. This is your output. And these are your assumption that this could contribute to those things. And you write down whatever you want to do. So for example, fatigue. Maybe when the person is fatigued, then they have this output. Then psychological workload and so on and so forth. So you put these things in. And you can realize that you can do it in anything in here. Then what you do, you throw this whole thing in a computer. And the computer's job is to, and oh, by the way, and you can connect them that these things may be connected to that, but what you don't have is a weight. Your expert knowledge or your physics knowledge or your understanding of the field is hidden in the arrow direction. The arrow direction will tell you that whether something is connected to something else. And in this case, it's not math. It could be a psychologist knows about this may be connected to that. So it's much more general than math. And so then what you do, you throw this whole network in the computer, and then there are the softwares like MOS and other softwares. And what it will do is that it will calculate the coefficients. And some of the coefficients may turn out to be based on this, when really doesn't exist, so your understanding was wrong. Or some of the coefficients may be one directional. You thought it's two directional, it's one directional. And once you have this, you can design your intervention. What can you do to make the nurse's life better? Right? Because you now know the hidden variable. Maybe you'll have an expert coming in and teaching them how to sort of have better posture, or maybe change the chairs that they sit in and all. So this is how many of the work in psychology and other places, those are actually done. And in fact, in chemistry, in biology, I removed two examples because lack of time. In here, it is extensively used when you're fast trying to do it. And most of the time, in research and other things, people have it in their head. They know they are doing it but they may not do it formally. Here is another example. The other example is, for example, solar cells. The reliability of solar cells is a big deal because solar cells, once you have bought it, it's like a free energy. And if it lives for 25 years versus if it lives for 40 years, then you get more energy out, and that's good. But it turns out that many of the components on the solar cell, they degrade over time. And so, for example, these are your input, ultraviolet radiation that's coming from the sunlight. The temperature, if you are in the middle in Qatar or in Saudi Arabia or this or that country, or if you are in deep in India or in Borneo or some other place, so you may have high humidity or high temperature or the combination thereof. And these are various components of a solar cell. For example, EVA is the encapsulant, and then you have a backsheet which holds the thing back. And then you have the, what is it, PET, polyethylene? I'm forgetting what the T stands for. But anyway, components of this. And then the physicists over the years, they have also understood that how things happen. For example, moisture can go in, there can be hydrolysis reaction. And so the experts in the area, based on the physics, or you yourself may use it. Meaning that you are reading a lot of papers, let's say. So you throw them in a box because here the physics is not known. So you throw them in a box, okay, this is a way of sort of organizing the papers that you are reading, that this may be connected to that, and so on and so forth. And then this connection, remember these arrows come from our knowledge of the field, and then these connections, there are in this particular case 7 connections. These connections are saying that this can be linear, like machine learning. Remember, straight line and all. Or it can be, so that's the first one, simple linear. But it could be quadratic also. This is something we did not have in normal machine learning. You could have exponential form. So this will essentially is bringing in non-linear connections. Remember, you probably asked, or I don't know who asked, that what if we have a circle? So this is quote unquote the circles coming in, which will reduce the network density. And then what you do? You throw it in a computer which optimizes all the coefficients A, B, C, and epsilon and all, making all this, given that you know the performance loss. This is your input, X. This is your output, Y. And this is your hidden layer. In the machine learning, it will be just a set of bubbles. But now, it is coming from your understanding of the field. And people put a lot of information about various experimental information in there. And at the end, they will have these coefficients. For example, these are, for example, A, B, C coefficients. That will come out of the computer. And the computer will tell. So you see, it's not 100% physics because you don't know the meaning of ABC. But nonetheless, this is reasonably better than pure machine learning because at least the intermediate points are physical. You can go and essentially check whether the intermediate points are physical, measurable or not. So, for example, this is the model they have done for ultraviolet radiation, that how the solar cell degrades in ultraviolet radiation. Damp it means that if you have a lot of humidity in the air, that how things go. And then this is done that way also. So, coming up with this network is the physicist's job or the person, domain expert's job, and doing it is the analysis of the job. And finally, you have these various combinations. So you can do pure machine learning, statistical. You can use this nonlinear one that I just showed. Structural equation modeling, you can do that. Or you can do physics-based machine learning, non-neural net. So this is the various levels of approximation you do for these things. So let me conclude with this, that I think machine learning is very useful, but for engineering problems, I think it's better to be a little bit more physics-based. And doing nonlinear coefficients are helpful, but you have to be careful about convergence, because some of the convergence proofs are not there, especially for large systems. So one has to be careful and I think it's very important to move away from the statistical model. Pure statistical model, I think that field is heading in the wrong direction. There'll be a lot of buzzwords these days, but it will be better if we make a better, more informed decision. So I'll stop here. You can take a quick look at the questions that have been posted in order to sort of